So it's now being recorded. So today we're gonna just basically cover what we talked about so far, in case you forgot already after the midterm, because any of these things I listed can go into the final exam. Don't worry too much about like maybe some of your friends are not here. I will do this Q&A again on the last day of class, but I want to do it now to kind of handle the question that you have so that we don't kind of like put every single question on one single day. So these are topic we cover so far for the second half, right? We will forget about well, okay, please don't forget about Linux and how to use C. Those are definitely a good skill to have. But in the second half, we talk more about what people would call computer organization. What does it mean? Basically, it means that it describes how computer works, right? How does it read the program? How does it read the data? How does it actually behave based on whatever language you are telling them to do? First of all, we cover data representation, right? This is uh, reflected in one of the in-class exercise where you have the input as in a bunch of character, and then based on that, you mark out the bits that you want as an output, right? So we talk about how do you represent a character. We talk about how to represent an integer, how to represent a floating point number. We also talk about what's the difference between signed and unsigned, right? How do I use the two's complement format? Right, basically this is based on the two's complement. And just quick thing, like basically you can do n, negative n equal naught of n plus 1. That's a two complements format. Logical operations, we covered this really quickly in class, and then on the assignment, you kind of like get bombarded with a bunch of like questions that ask you to use tricks with logical operations to kind of shrink how your program can behave with the same features, with the same output, but using logic operation because these are a lot faster, right? You can use, hopefully by now you know how to use and, or, X, or, not, and all the shifts, left shift and right shift. Any questions about these topics? Let me know right now. Let me know during office hours. I'm going to be here again in Discord at 7 p.m. I know that a lot of people are probably also crazy about the other homework from the other assignments, the other classes, right? Let me know if you need extra office hour next week, because the plan right now is Monday and Wednesday, but if you need more, I don't mind. Just let me know so that I can schedule the day that works for everyone. The next topic is program representation. What does it mean? When you write a program, those are all in English word-ish, right? Int something something, it's still using English letters. Computer doesn't know what are the English letters. They actually only know ones and zeros. The reason behind that is there are only two things computer can sense at the moment: high voltage and low voltage. That's why it maps really well with binary. Right? Zero, low voltage. One, high voltage. Then you construct everything based on the binary value, which means that your program eventually becomes a binary. The second part of assignment 3, you would then actually get to convert the bits, right, the binary into assembly, right? So this is basically assignment 3, part 2, right? Converting assembly into binary is kind of like the same. You have a switch case argument, read the assembly code. If this, then this is the binary. If this value becomes matching, basically it's a full-blown pattern matching. You can use that to convert your assembly code into binary. Programs are in the memory. So, for example, if I give you a block of binary and tell you this is where the program counter is pointing to. Can you extract what is the code that you're running if I give you what does each of the pattern mean, right? It's kind of like a follow-up of assignment 3 part 2. And then you just look at the block of bits a bit, right? And then figure out, okay, what is the code I'm looking at? This could be something that I ask you to do. Converting the assembly to binary is also another possible thing that I can ask you to do. Basically, this conversion between the program into assembly into binary, these are all like within the scope of this class. Then we talk about 86 assembly, right? How does it handle the basic compute operation, add, subtract, multiply, and then we talk about the memory operation, the move, right? Move with indirect access where you use a register value as an address. Think of it as that's how you can interact as you use something as a pointer. And then we talk about control flow operation, right? So these are the 3 fundamental types of operation on every single computer. Compute, memory, control flow. Control flow are basically if else and for loop. These are being implemented using jump and jump table, right? Condition code compare to check if something is true, jump, if not true, don't jump, go to the next line. We talk about the register files and the special register like the stack pointer, the program counter, or the instruction register. Those are the two. Those two has the same meaning. They are actually program counter. Function calls, how to handle function calls. What is a call stack? What happened when you call Fibonacci of 10? Basically, that's Fibonacci of 9 plus Fibonacci of 8, right? Which is the same thing as Fibonacci of 8 plus Fibonacci of 7 plus Fibonacci of 7 plus Fibonacci of 6. Then your call stack grow up quite a lot, right? How does computer handle that thing? Your memory is a straightforward address 0 to address 4 gigabytes, right? How do you actually maintain that call stack? So we covered that in the latter half of the assembly lecture. I believe it's assembly part 3 lecture. So if you're still like, hey, what am I talking about? Definitely feel free to ask now or check the lecture, ask the question during office hours. I'm going to be answering your question from as much as possible. All right. So these cover the assembly portion and the data representation portion. Then we move on toward the next set of topic, which is how do you manage the memory? Why do we need to care? Because memory is slow. It's not the end of the world to have to access the main memory, but it can be a lot faster if you can use the cache, right? So we talk about the benefit of caching. We talk about the how does cache get organized. We talk about the cache block, cache set, and cache associativity. We talk about the problem of thrashing, right? Where you have access to the same cache set, where these access kick each other out, so you never get a cache hit, even though there's a reuse in there. Then we talk about virtual memory, things like how do you translate from virtual address to physical address? What does it mean when I say page table? What does it mean when I say page walk? What does TLB mean? As I promised, that question would appear on your exam. What is a TLB? Then what is a virtually indexed physically tagged, right? What's the benefit? All right, so this is a scratch pad area where I'm gonna answer your questions. If I need to draw something, I'm going to draw it here. Any questions? Now is the Q&A part. If you're tired, I'm gonna leave it blank for maybe like 5 minutes until no one asks questions. Then I'll move on to the in-class exercise. Feel free to, if you don't want to type, turn on the microphone, that's fine. Let's make this a little bit more interactive. Okay, so the internal structure. So yeah, sure. So the question is, can I explain the internal structure of the TLB? Yeah, sure. So if you look at the TLB, right, it's going to be something like this. What do I need to maintain a TLB? So that would be my first question. What is the output of my TLB? The input obviously is a virtual address, right? So I get, yes, you get the physical address as an output. To actually get the physical address, what do I have to store in there? The actual physical address, right? So somehow you need to have that information. So let's say you're looking at physical address as something like this, right? 32 bits, bit 0 to bit 31. So whenever I put a number on top, it means that the bit position 0 and that's the bit position 31. Some of them are the page offset, right? The page offset is the same in virtual address and physical address, which means that there's no need to cache this part because it's the same thing. This part, we call it physical page number or PPN, physical page number, literally means that this is the number of my page in DRAM. The number goes from 0 to whatever the maximum value goes in here. So these think of it as, I'm gonna draw an analogy to the cache, right? Cache has the tag and has the data. The tag is used to search, the data is used as the actual storage. So the PPN goes in here, the data part, PN. To search for PPN, you have the virtual address coming in, right? So virtual address is going to look something like this, similar to physical address. You have the page offset. These two information are the same, right? And this is called the VPN, virtual page number. PPN is not the address of the page table, it's the address of the page. The page is, so if you look at so let me recap the question, right? The question is PPN the same as address of the page table? So PPN is, look at it like this. This is the structure of the page table. It's a tree-like structure, right? Then the leaf, the last node in the tree, that's the PPN. This is my page. And this is what PPN tell me. It's basically what the PPN tell me. Yeah. So that's the end product. Once you walk the page table, PPN is like the product of walking the page table. So to get the PPN, to get the correct PPN, what you can do is you can put in VPN here, right? So these are the tags. The VPN of each page would go in here. And then you might need a little bit more information. This is more like the OS side topic. That's why I don't like dig too deep into the TLB structure, but you will then also need things like what is the process ID to make sure that we don't have the synonym and homonym problem. These are the additional information you might need to put that into the tag area of the TLB. But at the end of the day, basically you are trying to map the VPN to get the PPN, right? So the VPN, go in here, you search the table. Oh, so that's a great question. The question is, I mean, the input is a virtual address, right? Why do I just store VPN? If I store the virtual address, it requires more bits. It's enough to store the VPN because basically you want the VPN to PPN mapping, right, to get the VA to PA. The reason behind that because the page offset is the same. That's known. I don't need to cache it. It means that I can make the TLB smaller, right? When I make the TLB smaller, because I don't need to cache every single thing here. I just need to cache the VPN fraction. and then the ppn fraction, right? When these are smaller, it means that I can add more entries. My TLB with the same size, I can have more items in there. It burns less power. Basically, when you shrink the input like this, it actually consumes less power. So this is basically more efficient to just cache the VPN. But does it answer your question? Yeah, so basically that's efficiency purposes. Basically, you want to build something that's efficient. You don't want to unnecessarily burn power, right? Think of it this way, like a motorcycle, right? You don't want to like put in too much engine. You're not gonna need them anyway. So yeah, why wasting this power? All right. So hopefully that answered the what goes into the TLB. Oh yeah, sure. Yes. So that's another great question. Since we have time, I'm gonna guide you through assignment three and what are the answer of the assignment threes, each one of them, especially the number of set bits. How many people finished that question? Figuring out number ones in my input. And there was like a one of you are asking something in the middle. Oh, yeah. Well, I mean, if the tester said you're correct, then it's correct. Oh, the PDF said it's two-way. Go with the .h file. Let me fix the PDF. I'm sorry about that. It should be four-way. Typo. Go with the .h file. Thank you so much for letting me know. I will fix the PDF. The PDF should be the same as the .h file. Stick with the .h file. Alright, I'm so sorry. Okay, so let me fix the PDF after this class. I'm gonna make an announcement to make sure that everyone is on the same page. That hey, sorry about the typo on the PDF. Here's the updated file. All right. Okay. Yeah. So what are you confused about in particular about the getting the set ID and getting the tag? Like as in like how or as in like uh, oh, yeah. So they work independently. It's the same address. So use the same input. The input is still that address, right? But you will then return the different bits. Wait, let me double check my starter code. Oh yeah, so let me fix one thing on the starter code. I forgot to separate out into two levels. So that should be L1, get L1 set ID and get L2 set ID, and then get L1 tag, get L2 tag. It should be separate on each of the level. Thank you again for that. I'm gonna fix it. Let me fix it right. Let me put a to-do list here so that I don't forget to fix it. Okay. Any other questions? So I remember. Oh no, I think I answered all of them. Can you explain the example given the bright function in detail? Oh yeah, sure. You mean assignment 4, right? Yeah, okay. So in assignment 4, the last task that you're doing is handling writes, right? So I hope handling read is probably pretty straightforward based on what we discussed so far, right? Handling writes is a little bit, just a little bit more complicated than handling read. So let's say you have the write to address 1, right? So basically you get the set ID, let's call it S, and then the tag. So I'll call it S1 and T1. So S1 is the set ID of address 1. T1 is the tag of address 1. All right, so you still with me, right? You get the set ID and the tag for both L1 and L2. So let's say this is L1, and then you have the set 1 L2, and then tag 1 L2. All right. So because you're accessing the cache, the behavior, let me double check that. So that seems to be an error to the init DRAM function. So let me kind of make sure I clean it up. So maybe I think when I clean it up last time when I have the functional code, I might have deleted too many things. Let me double check again. All right. So give me until the end of tonight to kind of resolve this. But yeah, thank you so much for letting me know of those. I definitely need to resolve those. Uh, so here is the two set IDs for L1 and L2. When you have a write, it's similar to the read in terms of insertion, right? When you bring in the new address, what do? You add them to both level, right? Both L1 and L2. So that's the first thing you need to do because you're accessing some data, some address. That address should be put in the cache. In this case, let's say this is the L1 cache, right? And this is the L2 cache. So you insert address 1 is inserted into both of these. You insert both address 1, you insert into both L1 and L2. Depending on the set ID, you go into that set ID. In the set ID in L1, how many items do you have to compare to? There are two ways, right? So there are two items. How do you pick what to kick out? Actually, it's FIFO. This is a even simpler policy. You don't have to update timestamp or anything. The only time you update the timestamp is when you insert, and then you pick the one that is the oldest, right? So in the struct called cache block, right? There is the data, there is the tag, and then there's also a timestamp, right? This timestamp you only update when you insert things into the cache. How do you update it? Just assign the value equal to cycle. Cycle tells you the time. We have that as a global variable already, so use it to basically keep track of time. When you insert this into the cache, you just compare the timestamp of the two cache blocks in the set in L1. Whatever is the older ones, kick that one out. So let's say you have cache block A and cache block B, and let's say B is older. Get rid of this, right? Get rid of it. Put this address data into here, the cache block, right? Do the same thing for L2. Cache block, I guess A, cache block B, cache block C, and cache block D, right? In here, whatever is the oldest get kicked out. So let's say D is the oldest, so you kick this one out, address one get inserted here. So are you with me so far? Basically, the insertion part, if the address is not in the cache, you just put the address in the cache. So are you with me so far? Basically, that's handling insertion and eviction. And this is the same as read. I'm gonna talk about what's the difference that you have to do for writes. Okay, so for writes, right? If you zoom into the cache block, so this is the cache block, right? A cache block is 32 bytes. That's our assumption from the assignment, right? Each data is 4 bytes, right? So this is what you do. 1, 2, 3, 4, 5, 6, 7. I need one more block right here, right? You need to figure out from the address, figure out which of these 4 bytes am I modifying. Basically, you get this address from DRAM. It will have some certain initial value, right? Based on whatever value, the address that you are writing to, you just overwrite the value into the cache block. So let's say address one want to write data one, right? And let's say address one is right here in the cache block. It's the 0, 1, 2, 3, 4, 5, 6, 7. So it's the fifth element in the cache block. So you put in data one. No. You put in data one here. So whatever the old data, just overwrite it. Right? So are you with me so far? Basically, you overwrite the data with the new data one. So that's handling the cache block. Then you just need to make sure you do these right on L1, L2, and then also on DRAM. Make sure you propagate the write on this address everywhere. And that's it. That's handle the write. Yeah, so basically that's a really, really high level overview of handling writes. Anything else should I add here to give you a hint? I think. Oh, okay. So what if it's an L1 cache hit? L1 cache hit, you don't have to do much. Basically, you skip the insertion, right? The cache hit, you can just skip the insertion. You don't have to do it anymore. It's already in L1. The only thing you have to do here is make sure you write the new data here in L1, write the new data here in L2, and write the updated data in DRAM. It sounds a little bit complicated. What will help you is draw this on the paper and kind of like put the step-by-step of things that you should do. Right? And then when you implement it, it's super straightforward once you list out the thing that you should do. So the steps, if it's a cache miss, bring in the data, insert them into the cache, evict the old data out. The eviction is just basically throw it out, overwrite the cache block. That's what you have to do. The next step is writing the data into the correct, figure out the correct bytes, the correct 4 bytes inside the cache block, overwrite that data, then make sure you overwrite it for both L1, L2, and their DRAM. And that's all. So once you list it out, it's actually pretty simple. If it's an L1 cache hit, skip the L1 insertion, skip the L2 insertion. You don't have to evict anything because the data is already in the cache. Just do the writes. If it's an L2 cache hit, then you put the data you insert into L1. it's the L2 hit, so you don't have to insert into L2. Then you write the data into L1, L2, and DRAM. That is a great question. So the question is like, you're curious, like if you do this, you kind of have to change the data for all three levels, including DRAM. Wouldn't that be slow? This particular caching policy is called write-through cache. If you go back to the caching lecture, that's a part that I said like handling writes. We are not gonna put this on the exam because it has some design decision you have to do. So that's a great question. The reason behind that is, yes, it wastes the bandwidth. You have to keep writing everywhere all the time whenever you have to write. There are policy that would avoid it. Basically, you would then update the L1. The next time you going to access this address, it would hit in the L1, right? Because it's already in L1. So you don't have to update the L2 because L1 would get a hit. You don't have to write into L2 until that cache block get evicted. So that would delay and save the bandwidth. That's why I said that's a great question. It's a legit concern. That's why most processors don't use this policy. It's simple. Basically, it's simple to implement. When you think about write, yay, write everywhere. When you think about read, just read from the data, and you don't have to care about, okay, do I write to L1? Do I write to L2? Do I write to DRAM? Just write everywhere once, and that's it. The other answer for your question in particular is, if you look at how you use the data, and then I guess if you, for one of you who taken the OPR already, like think data flow diagram. Basically, think of your instruction, right? The assembly code. Think of it as it's a function that takes data as an input, right? Data comes in as an input. The function would do like add, multiply, or something, produce a new data, which is an output, right? Input, which is the data. Input data come into your instruction that you add, multiply, or something. It produces an output. If you think about write, write doesn't cause what we call dependency. Dependency means that in order for me to execute or to run that instruction, right? To run that instruction, if I know that earlier instruction is a write, I know what is the data that I am accessing, right? So that data can feed directly into the assembly code, that particular line, so you can run it right away. So in terms of performance, write is not a big problem for the CPU. The main problem with write for the processor is more like these waste the cache bandwidth because you need to write everywhere, as you say. So I hope that partially clarify, or if not like fully clarify your answer, the question. Okay, so can I repeat eviction again? I'm going to use a clean slide then, because just so that it doesn't going to look too confusing. So what does eviction do? Eviction, it basically means that I have, let's say I have a box that can contain two things, right? I want to insert address, right? This address which contain the data and the tag, right? That's what you have in the cache block. So your cache block come in here, you have cache block. So let's say this is cache block A, this is cache block B, and this is cache block C. Right? And you want to put A into this box. And let's say cache block C is the oldest. What's the easiest thing I can do here? In terms of the simulator, I can just replace cache block C with cache block A, right? Cache block C is now gone. That's it. So just copy cache block A, overwrite cache block C. That's how you perform eviction. You just need to figure out which block are you kicking out, depending on who comes in first. Whoever come in first, they get kicked out first. Does it answer your question? Yes, by using timestamp, the only time you have to update the timestamp is when you put things in. So when you do this, right? When you put cache block A in, then you do this. You update timestamp. And when you look at who am I kicking, you just compare that timestamp. Yes. Exactly, yeah. So just simply assign the new address and the new tag and the new data into the cache block struct. That would work. That's why I initialized some of those for you. Basically, this was simplified a lot of things. You don't have to trace like, okay, did I initialize this cache block or anything? Yes, exactly. So that's another good question. So to look it up, it's basically looping through the cache, basically looping through the cache set that you found, the cache set, and check if the tag match. And that's it. Yes, that's all. That's the lookup function, right? That's why I will tell you now, it's actually a lot simpler than you think when you think about how caching works. Lookup is basically I'm gonna get cache set. I use cache set to see with the cache block structure that I have. That's a 2D array, right? For the L1 and the L2 cache. I get that row. When I get that row, I compare every item in that row. In the L1, there'll be 2 items there. In the L2, there'll be 4 items there. I check the tag. If it's matched, that's a cache hit. If it's not a match, cache miss. And that's it for lookup. And once you figure out, right, with the lookup, then the FIFO part, basically it's my attempt to make this even simpler. LRU, you would need to update the timestamp every time there's a cache hit, right? Because it means you access the cache. When you access the cache, you need to update the timestamp. With FIFO policy, the only time you update timestamp is when you put this new cache block into the cache. It's first in, first out. If you stay in the cache, you don't have to update the timestamp. You only update when new things come in. Let me make it more concrete. Let's say my cache L2 cache is something like this. You have cache block A, cache block B, cache block C, and cache block D. And then your access pattern is A, followed by B, followed by E, followed by D, followed by F, right? And this is what would happen with the FIFO policy. When I access A, okay, cache hit, that's fine. Oh, and let's assume this is the oldest, and this is the newest. So A comes in, cache it, fine, I don't do anything. Cache it, yay. B comes in, cache it, yay. Don't have to do anything at all. No eviction, you don't have to do anything. E comes in, it would then search, right? Lookup would say, hey, cache miss. What you have to do here is to compare the timestamp of A, B, C, and D. So which one is the oldest now, based on the timestamp? A, yes. Even though I accessed A earlier, it's a FIFO policy, so I'm not going to update the timestamp, so A still remains the oldest. So I'm going to kick A out, replace it with E. B becomes the oldest. E becomes the newest. So when I access B again, it's a cache hit right over here. Don't have to do anything. F come in, which one do I kick out? Yep, B. Yeah, so you kick B out, you replace it with F, and that's it. So keep basically then loop over until, so if it's an LRU, this is what happens. So this is FIFO. Right? I'm gonna show you what happened when they have the LRU. So this is LRU policy. Right? Start with A, B, C, and D. A, B, C, and D. Oldest, newest. You access A, cache hit. These become the newest because you just access them, right? B become the oldest. Then you access B, cache hit again, yay. So this becomes the newest. What becomes the oldest? Yes, C becomes the oldest. So when you have access to E, because C is the oldest, it kick out C, replace it with E. E become the newest, and now D become the oldest, right? Then you have access to B again. So B, E no longer become the newest. Now it's B become the newest, right? And D is still the oldest. So when you have F come in here, F replace D. So that's the difference between FIFO and LRU. And as you can see here, FIFO is actually simpler to implement in the simulator. Why? You don't have to update the timestamp. The only time you update the timestamp is when you put things in. All right. Basically, up on cache hit, you don't have to do anything. Except if it's a write, then you update the data. That's all. Okay. So any other questions? Otherwise, I'm gonna go through the in-class exercise 11, which is basically virtual memory and address translation. So to kind of make it simpler to see, let me unshare my screen and bring up the PDF. So I'm gonna do it on the screen for you for one of the question. All right, so do you see my screen? All right, awesome. So if you might want to guess, this is the exam from the previous semester. This is one of the question, and I think it's worth one of the most points from the previous semester. So let's go through them. It's related to virtual memory. So now let's look at, okay, what is this? Assume a 32-bit byte addressable machine that has 4 megabyte page size, 1 level page table. What is the number of bits required? Okay, that's a good question. Is this going to be similar in the final exam? It will probably be similar in spirit, but definitely not the same question. Right? I'm not the type to reuse the exam. Even though I reuse the assignment, I don't reuse the exam. It's a 32-bit byte addressable machine, 4 megabyte page size, 1 level page table. So what's the number of bits I need for the page offset? Can someone tell me the formula for this? How many bits do I need to tell all the address within this 4 megabyte range? Exactly. Log of 4 megabytes. How many bits are that? 22. Basically, 10 is 1 kilobyte, 20 is 1 megabyte, and you multiply 22 more times. So that's 4 megabytes. I will give you the log table at the end. Don't worry. So from the previous exam, I also do the same thing. I will be happy. I include the table saying log of this equal this, log of this equal this, and it's a big table. Assuming that the index bits for each level of the page table are divided equally for one level page table. I don't even know why I need to put it here, but it's actually basically tricky part where it's like, why are you dividing? What's the maximum number of page table entry you can have per page table here? You have one level of page table. You have 32-bit address. How many bits do you have left after the page offset? So this is page offset, right? 22 bits. So how many do we have left? 10 bits, right? So 10 bits. With 10 bits, how many page table entries can I have? It's actually 2 to the 10, right? Because you have 10 bits. Each bit can be 1 or 0. So that's 2 to the 10. Yeah. Be careful, don't make me feel too sad. If you answer 10, I'll give you some partial credit, but I'll be super sad because you got I know you got almost the right answer. With all the above assumption, what is the maximum number of physical memory that my system can support? So you can have 1024 entries, right? How big is each entry? Yes, exactly. The answer is you have 1024 entries, right? Each entry is 4 megabytes. So that's basically 4 gigabytes, right? And with this assumption, what's the maximum capacity that I need for my page table? How many page table entries do I need right now? But why is 1? I have 1024 entries, so I need 1024 something, right? So it's 1024 multiplied by, so if you go down, you'll see that the page table entry is 32-bit long. So it's basically you need to read like all the question together. So this is basically 1024 multiplied by 32 bits, right? So if you want to get the answer in bytes, so you divide everything here by 8. So that's 4 times 1024 bytes. And that's the answer for how big is my page table. All right, so that's the easier part of the exam. And it gives the hints of what's going on here. What I'm saying here is I would assume the page table root is at address 0, which is right here. Right? My page table is 32-bit long. Basically, that's 4 bytes. Each one of these numbers 1 byte, because I group it based on the hexadecimal number, 2 digits is 1 byte. Oh, you can leave the. So that's another question is can I just leave the number like this? Yeah, fine. You don't have to calculate it. I don't want to okay. If you get the formula correctly, things like log of 4 megabytes, that's okay. I would believe that you can type, if you need that for your work, I believe you can type that on your calculator to get the answer. So I don't care if you need, if you get the exact number. But if you leave the formula, you need to, and it's not obvious, you might need to tell me what you're doing. Most of the time, it should be pretty obvious unless you're doing something wrong. All right, so let's go to this question. Page table is 32 bits long. Oh, 8. Okay, so the question is where 8 come from again. 8 come from, we have, each one is 32 bits. I just want to convert to bytes, so I divide everything by 8. Sorry for that confusion. Basically, I just want to convert bits into bytes. All right, so this question basically, oh, can I repeat question two? Yeah. This one, right? Okay, so this one basically, we are asking that how many, if I have the 32-bit virtual address and I assume 4 megabyte page size, one level of page table, right? Which means that the page offset would take 22 bits. How many page table entries, right? How many page table entries in that one level page table can I have at maximum? I have 10 bits left, right? I have 10 bits left for my virtual address. It means that I can only tell 2 to the 10 different locations, which means that the maximum number of page table entry for my page table is basically 2 to the 10. If I have 1025 entries, how can you differentiate between the 0th entry and the 1020, the last one, basically? Exactly, yes. So it's 32 minus 22, and then it's 2 to that number. All right, so let me do this quickly here. My physical address is 32 bits, right? So given this table, how can I tell what is my physical address? Let's do the first example. This is my first example, dead beef. Which bit do I take in order to get the index into the page table? So what is dead beef? F is 1111, right? What is E? 1110. What is B? 1011. D is 1101. This is 010, 1110, 1101, right? Which bits here am I taking for the virtual page number? Which bits are the page offset? 0 to 21st, right? 0, because we need 22 bits for that. From the earlier question, right? You need 22 bits for the page offset. 4 bits, 8 bits, 12 bits, 16 bits, 20 bits, 22 bits. This part is the page offset. This part 1101, 1110, and 10. This is the index into my page table, right? With this information, can you tell what am I looking at? But basically, what is the entries that I want to refer to? If you do this conversion, you will notice that these alone is 2 to the 9. 2 to the 9 is something like 512, right? So you are getting some tail end of your page table, your tail end of the page table. These, oops, US. For this data that I provide you, this is entry. Let me use a different color to make it a little bit more easier to read. So this is entry 0. This is entry 1, right? This is entry 2. How can I tell that? I make that assumption that page table entry is 32-bit long, which means that this is entry, the fourth entry, the fifth entry, the sixth entry, 7 and 8, right? So if you think about it, this is what you get. This is index 0, index 1, index 2, index 3, index 4, index 5, index 6, index 7. I have 16 of this row from address 00 to F0. It means that I basically count 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, A, B, C, D, E, F. There are 16 of those numbers. So what is the index of these last entry that I show you on this table? If you do this math, is 63. Oh, how can you know the entry? Good question. So basically, it's in the assumption here. I said entry is 32 bits long. Right? It is 32 bits long. And I said the root is at this address, 00, right? It means that that's my 0 entry. And I just start to go from there. So that's how you can tell the entries. But based on just this table that I'm giving you, you will then notice that, hey, this is definitely way greater than 63, right? So this means that I don't have enough information. Oh, that's the data. That's the data. So if you go to the next question, I'll tell you why do you have that value. So the next question is, what if I look at this address? Oh, why do I select 4-bit as one index? Because I assume that entry is 4 bytes long. Here's my assumption. Entry is 4 bytes long. It means that I need 4 bytes for each entry. So the yellow block comes from the fact that I tell you in the exam question that said, hey, my page table entry is 32 bits long. So I would then group, right, based on the starting point. The starting point right now is address 0. I would group that in a group of 4 because I know that a group of 4 is one entry. All right. So let me kind of redraw. Maybe that would be a little bit easier. So this is your page table, right, from top to bottom. Entry 0, entry 1, entry 2, entry 3, entry 4. Right. This is address 0x00. With entry 1, where's the starting address? I know that this entry 0 is 4 bytes size, right? So the next starting address, I need to add 4 into that. Otherwise, you have overlapping data, and that's not good. So you have to have 4 bytes for each entry. So this started 0x04, 0x08, 0x 0c, 0x10. right? So you know that each of these yellow block, which correspond to the page table entry, the block that correspond to the page table entry, is going to be 4 bytes. So entry 0 would be in this block, entry 1 would be in this block, entry 2 would be in this block, just because you know it's 4 bytes. So that's it. Is it clear now for you that why do I group by 4? Yeah, basically it's because of this assumption that I say, hey, it's 32-bit long. I need to tell you that, or I need to give that information to you somehow in the question. Yes, it's a matter of finding the correct set of bytes for your address. So I'm gonna do the next example because this one you would need to use the table, right? So what is 0x 0f f f f blah blah blah? If you do the same breaking down, right, you then notice that this part is 0 0 0 0 1 1 1 1 1 1 1 1. You know that you're taking the last 10 bits, 4 bits, 8 bits, 9 and 10. So your index is 0 0 0 0 1 1 1 1 1 1. What is that number? This is 1 plus 2 plus 4 plus 8 plus 16 plus 32. Someone please correct me if I'm wrong. Let me double check. 1, 2, 4, 8, 16, 32. Yeah. This is essentially 63. Do I have the entry number 63 in my table? Do I have entry 63 in my table? Yep, I just draw it right here, right toward the end. So you know this is the entry for address 0x 0f f f f f, right? So what is that value? Let me help me remember actually. 6b12, 6b12, 4b31. I need to remember that number. So let me copy that over. 6b12, what else? 6b12, 4b31. Right. This number should be the same as this number. That's your value in the page table entry. You know that your page offset is 32 bytes, 32 bits. Oh my God, not 32 bits, my bad. 22 bits. How do I get that? Here, the answer is right there. 32-bit is page offset, right? So you know that, hey, from my address right here, the last 22-bit go into the page offset of my physical address. How do I get my physical address? So your physical address, right? What does it consist of? It consists of page offset and the physical page number, right? Are you with me so far? Basically, your physical address consists of page offset and the physical page number. What is a page offset for this virtual address? So this part is VPN, right? This part would be the page offset. The last 22 bits, exactly, the last 22 bit of my virtual address. What is that? It's just a bunch of ones. That's why I just left a bunch of F's because you don't have to really compute anything. It's a bunch of ones. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22. Okay, I cannot count. I think we are all tired right now. How many bits do I need left? I have 22 bits now, right? I still need 10 bits. I still need 10 bits. Where can I find that 10 bits? I get it from here. How do I tell which one is that? So if you look at this page table entry, 6B, 1, 2, 4B, 3, 1 is the 10 bit starting from this side. So what is 6? 6 is 0, 1, 1, 0. What is B? B is, what is B? 8, 9, 10, 11. 1, 4, 1, 0, 1, 0. And what is 1? 0, 0, 0, 1. Is that enough for 10 bits? Yes. Which one are those 10 bits? 0, 1, 1, 0, 1, 0, 1, 0, and the rest 2 bits is from the letter 1. Okay. So this is your physical page address. So you put it here, 0, 1, 1, 0, 1, 0, 1, 0, and 0, 0. So that's your physical address. The last 22 bits come from your virtual address. The left part of this, the physical page number, come from the most significant bits in your page table entry. All right, any questions about this? All right, cool. So I recommend you to redo this one more time now that you know how to do it. Oh, yeah, it would be great if you can convert at least up to the letter F into binary. If you want me to put that table, actually, okay, let me put it this way. If you want me to put a conversion table, you need to tell me maybe a few, okay. Can you remind me next Wednesday? Just so it's not like I don't want to put it in. I just want to make sure I remember to put it in, right? I just want to make sure I remember to put that table in. So please remind me toward the end of Wednesday, so that, hey, I don't forget to put it in. Okay, so the one more question is, if the page table entry is 64 bits long, how many bits would be the one that go into, what do you mean by would be one index? I'm trying to understand your question. Are you asking about the number of index bits, or are you asking about what if it's 64 bits long, which one is the PPM? Oh, yeah, then it would be 64 bit in one block. If it's 64 bit long, then this yellow block would span eight bytes. Right now it's 32 bit long, so I'm gonna basically that means that it just spanned 4 bytes. Yeah. So this is one of the question that if you've never seen it before and you kind of like, hey, I need to kind of like work through the page walk, this would look intimidating. It's just so much raw data given to you. But if you know what you're doing, it's actually really straightforward. You find the correct byte you want to look at, you grab that byte, extract it, done. All right, so basically that's it for the in-class exercise for today, I think. Is there more? Oh yeah, there's one more question about translation look-aside buffer and the VIPT. So I'll leave it as leave it for your practice actually. But yeah, so one of your friends comment right now is like, yeah, I think it's easy, but it's too much information. I agree. That's why I said when you look at this table in the first place, like it looks extra intimidating, right? But at the end of the day, you can break it down to something super simple, because that basically computer design is like how to make it simple so computer can work, right? Um, The rest of the question is about VIPT and the TLB. I'm gonna leave it for you to solve it, and I'm not gonna give you this already correct worksheet so that you go through the questions again on your own. I think that's the best way to kind of understand how this works because there are way more office hour and then 2 more classes coming up. If you run into any of those questions, I'd rather have you ask it before you take the final exam. And this is hopefully a forcing function on how you can get practice before the final exam. Yeah, the final exam is on Wednesday, 22nd. Wednesday of the final week, 22nd. All right, so anything else? Oh, okay, that's another good question. Is it going to be equally assembly and memory part? I think so, actually, because is equally important. But the assembly part also include data representation, right? Things like, okay, how do you represent character? How do you represent integer? How do you represent sign and unsigned? Uh, so it's a mix of those two. It's not like I'm gonna ask you to like write 10 assembly code. All right, so I'm gonna leave the meeting on my laptop and join them, like remain on the meeting on my desktop. So there might be echo noises. I'll fix it real quick. Mute. Okay, so I'm back. Let me save the files. Oh, the practice is from in-class exercise. It will be the same level as the in-class exercise that you did actually. If you remember way back, right, that you need to do the jump table and handling like function calls, and that's the type of question I'm asking you. It's not gonna be that more like much more complicated. It should be pretty straightforward. Trust me, that's I grading assembly question, if it's too complicated, it's impossible to grade. Trust me. Happened to me before while I was a TA for CMU. Uh, the level of assembly question would be roughly the same as the in-class exercise. And then the data manipulation and the logical question, like the logical operation questions, there might be something similar, not definitely not the same as the assignment, right? But something along that chain of thought, along that difficulty, could be asked. Not the hardest one, obviously, because the hardest one I designed it so that you would think about it over the range of days, right? But if you should be able to tell like things like, okay, what do I do if I want to like say multiply by 2 to the 4 and then do some a little bit more tricks to it, right? How can you use logical operation to optimize it? I think that's all for the exam. Yeah, and the deadline. So the deadline for the last assignment is actually It's 23rd without using the token. If you still have the token left, it's 24th. And because I need to submit the grade to OAA by basically I think the policy is like definitely a week before 1 week after the exam date. If OAA actually schedule my exam on Wednesday, I like plan, right? And basically our exam will be on Wednesday, but OAA can say whatever. Basically our exam will be on Wednesday class time. If OAA say, hey, your slot is Monday, it means I have to submit that grade to them on Monday, which means that I have like 2 days to grade the assignments. So that's literally like I think that's realistically the last day I can like I can extend it for you. This is like the last day possible that I can do. So basically you can do 24th midnight if you have the token. And yes, I would help you through each question on assignment 3 in the next lecture.